All right, today we're going to learn about local linear approximation and differentials. Don't confuse that with local linear approximation because that would just be crazy. Now, we have a new formula. Don't get scared. We've actually known this formula since we were in Algebra 1. Let's talk about what it means. First of all, local linear approximation basically is the idea that if you choose a point, any point on a curve, and zoom in enough times, and you could do this with your own graphing calculator, zoom in over and over and over again, eventually it doesn't look like a curve anymore. What does it look like? You guessed it, it looks like a straight line in that little place, in that local area. It looks like a local linear piece, meaning if you zoom in enough, your curve looks like a straight line in that one specific point. And say we call that point x0, comma, f of x0. And maybe the slope of that line is called f prime of x0. This should all be notation that you're familiar and comfortable with. So slope. If we were going to find the equation of that line now, we would use our Algebra 1 formula, y minus y1 equals m x minus x1. That formula should also look totally familiar. You should be comfortable with it. You've probably hung out with it a lot in the past. So we're going to plug things in. Our y1 is f of x0. Our m is f prime of x0. X minus, our x1 is really x0 on this problem. And let's not call that y. We have another name for y we could call f of x. And just for fun, why don't I add this f of x0 to both sides? Because we're allowed to add something to both sides of an equation. We've been doing that forever. And then we end up with f of x equals f prime of x0 times x minus x0 plus f of x0. And since this is actually not a straight line, but it's just kind of like a straight line, we won't say equals here, we'll say approximately equals. And hey, what do you know? That's the exact same formula that I'm telling you that you have to memorize. I'm using air quotes when I say memorize. You just can't see them. You don't really have to memorize it. It's really just your point slope formula from Algebra 1. That being said, you do need to know. You're going to be able to need to use it. You're going to need to be able to use it. So let's look at something. Let's find the local linear approximation of f of x equals square root of x at x equals 1. Notice the local linear approximation changes at different points. At x equals 1, I have that line there. If I were to choose a different point, it's a totally different line. If I chose a point close to 0, totally different line. That's why when we're doing local linear approximation, that word local is key. We're only looking at a specific x value. The linear approximation gives a clue. It means we want an equation that is a line. You guys know what a line is. So let's put our formula into effect. First, I like to write down my formula. F of x is approximately equal to f of x0 plus f prime of x0, x minus x0. There's a lot of things in this formula. I need to know what f of x0 is, which means I probably need to know what x0 is. In this case, it's 1. Now I can figure out f of x0, which really means f of 1, which really means square root of 1, which is 1. What else do I need? I need the derivative at x0, which means I need the derivative of f. If I want my derivative of f, going back to the original equation, we should be able to figure out without too much difficulty that the derivative is as so. Now if we want the derivative at x0, which again is really the derivative at x equals 1, we just plug in 1. and we get 1/2. Looking at my formula, I already know x0. It looks like I know everything now, so I'm going to plug it all in. Let's color code for your convenience. We want f of x0, which is 1. We need f prime of x0, which we just figured out was 1/2. And we need x0, which is 1. Plugging all of that into our formula, we get f of x is approximately equal to f of x0, which is 1/2, plus, I lie, f of x0 is not 1/2. F of x0 is 1, plus f prime of x0, which was the 1/2, x minus x0. And we've got our equation of a line. Could I clean that up? Absolutely. Do I necessarily have to? Not really. But why not? 1 plus 1/2 x minus 1/2, which is really 1/2 x plus 1/2, which, yes, is a straight line. That's key. This is local linear approximation, so our approximation line needs to actually be a line. So that's it for part A. Part B says, use the local linear approximation to approximate the square root of 1.1. And this is where this is kind of cool. We're going to try to figure out f of 1.1 without a calculator, which really means the square root of 1.1 without a calculator. Thanks to our local linear approximation, first we decide, is 1.1 close to the number that we decided to use, which in this case was 1. 1.1 is pretty close to 1. So we get to use our local linear approximation formula. Plug in to this guy right here, 1/2 times 1.1 plus 1/2, which is really .55 plus 0.5, which is 1.05. And go ahead and pause the video and try to think of a great way to check to see if this answer seems reasonably close to the actual answer. I will tell you how to do it in 3 seconds. If we want to know if this is accurate, we can actually put into our calculator square root of 1.1 and see what we get. And in my calculator, I get 1.049, which is pretty darn close to 1.05. So let's step back and realize the power of what we've just done. We just calculated the square root of 1.1 without a calculator. Now that's not necessarily useful in all situations, but there's going to be some cases, and I think we'll see one in this lesson, where we would not have even been able to do that with a calculator. So let's move forward. Example 2. Let's find the local linear approximation of f of x equals sine x at x equals 0. So again, we start with our formula. We need to identify all the pieces. Then we're going to plug them in. Using example 1 as a model, I want you to try this on your own. I'm going to put up my work for you to check your work. Go ahead and pause the video and try it. Hopefully you should have come up with the equation f of x is approximately equal to x. Part B is a little tricky. It's asking you to find sine of 2 degrees. But we're not allowed to use degrees in calculus unless we do some conversions. We like to use real numbers without units in our trig functions. So we don't want this in degrees. We want this in radians. So our first step is to figure out what 2 degrees is as a radian. If you don't remember how to do that, we just use a conversion. How many degrees in a radian? Or how many degrees? Yes, that's right. 180 degrees is how many radians? Pi. Degrees cancel out. 2 and 180 cancel out. Pi over 90. So we're really talking pi over 90 radians. Okay, so we're going to approximate sine of 2 degrees. So let's see what that looks like. Well, the approximation formula is pretty simple. If we want to approximate f of pi over 90, that would approximately be pi over 90. And by the way, we're only allowed to use numbers close to 0. Pi over 90 is close to 0. If you don't believe me, how would you like to get 3.14 out of 90 on your next test? Pretty close to 0. So there's our approximation, which we can get as a decimal. Turns out that it's 0.0349 if you put that in the calculator. Now if we actually go to the original function, f of x equals sine of x, and calculate sine of 2 degrees, or sine of pi radians, pi over 90 radians, put that in the calculator and we get 0.0349. Pretty close to the same thing. In fact, rounded to 4 decimal places, it's exactly the same thing. So our local linear approximation seems good. Okay, time to throw some notation at you. dx can be thought of as the change in x. And change in x and dx are kind of interchangeable terms, whereas dy and change in y are not quite the same thing. dy is the change in the y on the tangent line, whereas delta y, that's a Greek letter by the way, is the change in y in the function. dy and delta y are not exactly the same thing. Now, let's talk about this formula for a minute. We know dy dx is the same thing as f prime of x. To get that formula, all we did is multiply both sides by dx. So let's see what I'm going to try to lead us to right here. It says express the derivative with respect to x of y equals x squared in differential form. And differential form just means having all the y's on one side, all the x's on the other side, including the dy and the dx on their respective sides. So if we took the derivative of y equals x squared, we'd get dy dx equals 2x. We want all the y's on one side, all the x's on the other, so I've got to move this over. dy equals 2x dx. And we want to discuss the relationship between dy and dx at x equals 1. If I plug in my x equals 1, I end up with dy equals 2 dx. What this tells us is at x equals 1, for every change in dx, there are 2 changes in y. So if we look at that on the tangent line, if I change my x by 2, that means I should change my y by 4. If I change my x by 1, I should change my y by 2. It's telling me that the y is getting big twice as fast as the x on my tangent line. That doesn't tell me how much y is changing on the actual curve. It's getting big even faster. But the tangent line is changing in such the way that y gets big twice as fast as x. And that's kind of what you need to be able to take away from this. If I change x by 1, I have to change y by 2. Let's look at this another way. It says y equals square root of x, find dy and delta y at x equals 4. Remember, dy is the change in the tangent line, change in y on the tangent line, whereas delta y is the change in y on the curve. The further we get away from the point on the curve, such as right here, the point where the tangent line touches, further we get away from that, the bigger difference there likely is to be in dy and delta y. So let's find dy. That means we're going to find a derivative. Dy dx equals 1 over 2 squared of x, simple derivative. Get it in differential form. And the point we care about is x equals 4. So at x equals 4, dy would equal dx over 2 times the square root of 4, which is dx over 4. The problem tells us that we're interested in a change in x of 3. So I can put in my 3 for dx. And my dy is really 3/4. Let's talk about what that means in the graph. We happen to have the graph right here on the slide. So at x equals 4, if I move my x over 3 units, that's my dx, then my dy started at 2, because that's what y equals when x equals 2, and now we moved up 3/4. And that touches the tangent line, not the curve. Notice the curve is a little lower than the tangent line. The distance from 2 and the curve is 2.75, which really means this point we should be able to figure out is 7 and 2.75. It's not what it's asking us. It's just asking us how much did y change on the tangent line. Looking at that picture again, I'm going to erase what I just wrote. If we're actually trying to find delta y, which is the change in y values, which is the actual curve, we can see on the picture that it should be less than 0.75. It tells us in the picture that it's 0.65. Let's figure out how we know that. We know that this point on the curve would be 7 comma square root of 7. Square root of 7 in a calculator happens to be 2.65 approximately. So now we can figure out our change in y. Our new y is 2.65. Originally, y was 2. So change in y is 0.65. So my whole point with these last two examples is to kind of explain the difference between dy and delta y. And to recap that major idea, dy is how much your y changes on the tangent line. In this case, this was 0.75 between 4 and 7. So in this little interval, my y went up 0.75 on the tangent line. Delta y is the change on the actual curve. The curve went from 2 to 2.65. Not quite the same. Derivatives. This is really telling us stuff we already know. I wouldn't even worry about it at all. It's just the different notation. Do your quick check exercises. Coming to class without your quick check exercises means you don't care about being excellent. And that's not you. You are so much better than that. Have a wonderful day.